Hey guys, Andy here with Greenbelt Academy, and I'm incredibly excited for another video today where we are going to cover another important topic on the Greenbelt exam and the Black Belt exam, and that is design of experiments, or DOE. And by the way, if you're preparing for either one of those exams, stick around to the very end where I'm going to share a free resource to help you prepare for the Greenbelt exam or the Black Belt exam. All right, let's head over to the computer and get started.
All right, let's get started. And, before we jump into the details, I love to start with context. So if you're preparing for the Greenbelt exam and you go to the body of knowledge and you look up this topic of DOE, what you're going to find is that there are a bunch of terms and definitions and principles that you have to know to be successful on the Greenbelt exam. Things like independent and dependent variables, factors, levels, responses, treatment, error, repetition, blocking, randomization. A lot of core terms and definitions make up the bulk of what it means to be proficient in the terms or in the area of DOE. Now, the reason I picked DOE, by the way, is because not only does it apply to the Greenbelt exam, but it also applies to the Black Belt exam and the CQ exam. And a lot of the same concepts that we find on the Greenbelt body of knowledge, you'll also find in the Black Belt body of knowledge. The same terms: independent, dependent variable, factor, level, response, treatment, error, design principles like repetition, order, randomization, blocking. There's a lot of core principles that span a bunch of different exams, as well as, if you're going to be a Black Belt, how to actually plan out an experiment, right? What are those 7 steps to actually designing a thoughtful experiment to solve a problem or to optimize a process? Now, this same content also applies to people who are preparing for the CQ exam. And so all those same terms like variables, factors, levels, responses, treatment, error, replication, those same terms and design principles like replication, order, randomization, blocking. A lot of the stuff we're going to talk about today applies to the CQ exam as well, along with how to actually plan out an experiment. And so that's what I want to cover today. I want to teach the basics of DOE. What you'll notice here too is whether you're dealing with the Black Belt body of knowledge or CQE body of knowledge, it's a big topic. There's a lot we're not going to talk about today: fractional designs, full factorial experiments, main effects analysis, interactions. There's a lot of terms we're not even going to talk about. Confounding effects. That might be a subject of a future video. If you're interested in that, leave a comment below and let me know what you're interested in learning about, and perhaps we'll make a video in the future for some of those topics. In terms of today, though, I want to start with why. I want to start with understanding when or why, as a quality professional or continuous improvement professional, when and why you would want to use a DOE to help you solve a problem or something like that. And then as we go through it, we're going to start talking about a lot of the most important terms and definitions in the world of DOE: factors, responses, levels, treatments. I want to explain what that all means. If you're going to design an experiment, you have to understand these important topics. And again, if you're going to design a thoughtful experiment, you have to be aware of important design concepts like error, blocking, and randomization. We're going to spend a lot of time talking about the 2 different types of error and how we can use blocking and randomization to address that type of error. And then along the way, we're going to go through the 7 steps to design a DOE. Actually, in truth, I'm only going to cover the first 3 steps. I think these are the most important 3. But again, if you want to see a future video on, the back 4, the last 4 steps in the DOE process, leave a comment below and let me know, and maybe we'll schedule a future video. Okay. In terms of the DOE process, this is kind of the Simon Sinek advice: start with why. You want to start by understanding why you're exactly going to do a DOE. And there's tons of different reasons in quality or in continuous improvement when a DOE is the right tool to use. Maybe you're doing root cause analysis and you need to identify the root cause of a problem. Or maybe you're trying to optimize a design or a process to improve yield or some quality attribute or something. Maybe you're reducing cost. Maybe you're improving OEE. There are a ton of different reasons. Now, it's important for you, before you ever start your DOE, to sit down with your team and make sure that everybody is on the same page about the experimental objective that you're trying to achieve. Why are you doing a DOE? What is the problem statement that you're trying to solve? What is the objective of your experiment? That discussion, that experimental objective will drive a lot of the decisions that we make as we're moving through the process. What factors do we study? What factors do we block out? What output do we want to measure? What type of design do we want to use? A lot of major decisions that we make along the way depend on the type of experiment that we're going to run. For example, if you're optimizing a design, that's a completely different experiment than if you're trying to identify the root cause of a problem. So again, the first step in a DOE is to make sure you and everybody on your team, because it's a team sport, everybody understands that this is the objective we're trying to achieve and this is the problem that we're trying to solve. Okay? Now that you have kind of the why, I want to take a step back and I want to explain how DOE kind of fits into the world of quality and continuous improvement. And I want to explain it using a quote from Dr. W. Edwards Deming, who said, "If you can't describe what you're doing as a process, you don't know what you're doing." Okay? And according to Deming, every activity in business, whether it's a manufacturing process, an engineering process, a design process, a sales process, every activity that we engage in can and be viewed as a process. In fact, he gave us what we call today the process model. Every process starts with inputs. We take those inputs and we feed them through a sequence of steps. And then at the conclusion of that process, what we get are outputs. Okay, this is called the process model. Every activity that we engage in life and business can be viewed as a process. Now, this gets back to kind of why do we do a DOE? A design experiment, or a DOE, is essentially a statistical method that we use that allows us to identify and quantify the relationship between the inputs and the outputs of our process. In fact, the other quote that I like to give people is that your results are only as good as your process. If we want great outputs, we have to have a great process, we have to have great inputs, and so we need to understand this relationship between our inputs and our process and our outputs. Okay. Now, this gets us into some really important terms and definitions in the world of DOE, and let's kind of start with the end in mind. Let's start with our outputs. In the world of DOE, these are often called the response variable or the dependent variable or even just the Y parameter. And I prefer the term response variable because the way I like to think about it is your outputs respond to changes in your inputs. If we change the inputs, our outputs are going to respond to that change, right? That's what we mean when we say a response variable. Now, this could be a ton of different things. It could be your dimensional attributes, length, width, height, some feature, whatever. Your dimensionals are an output of your process. It could be yield. Your yield is an output of your process. If you have a bad process, you're going to have bad yield. If you have bad inputs, you're going to have bad yield. The same thing is true as if you have a great process, you're going to have great yield. Product functionality, lead time, the cost of your product, for example, is an output of your process. It is a function of your inputs and your process, and that determines the cost of your product. Same thing is true with OEE and process capability. These are all outputs of your process. And the point of a DOE is to get better. We want better outputs. And to have better outputs, we need better inputs and we need a better process. Okay, so that's what we mean when we say outputs. The other side of this equation are the inputs. And in the world of DOE, the term that you're going to hear the most are factors. These are factors in our experiment, variables that we're going to change or control. And then what we're going to do is we're going to change these variables and we're going to measure how our output changes in response to the changes in our factors. Okay. And so again, if you see that term factor, all we mean is an input. It is some sort of independent controllable variable that we're gonna change. We're gonna vary that parameter and we're gonna measure the impact that that change has on our outputs. Okay, so that's what we mean when we say input variables. In the middle here, in the middle of the process diagram, is the process itself. This is a sequence of steps that we go through to take all of our inputs and transform them into outputs. Okay. Now, the reason that we start with these definitions too, by the way, is because it relates back to the process of designing an experiment. If you're going to design a DOE, once you have your experimental objectives, steps 2 and 3 in the process is to essentially sit down with your team and identify the outputs that you're going to study and the inputs that you want to include in the experiment. Okay. And I'm going to show you a tool here in just a second to help you clearly define all of your outputs and your inputs to design a thoughtful experiment. But before we do that, I have to make a comment about your measurement systems. Okay. Think about your outputs, dimensional attributes, product functionality, process capability. You are going to measure your product or process in some way. You're going to take a measurement using a measurement system. And for those results to be valid, your measurement system has to be both accurate and precise. And so again, when you're designing that experiment, make sure that your measurement system has the gauge R&R necessary to measure whatever feature it is that you're studying. If not, that loss of accuracy or that loss of precision will introduce error into your experiment and essentially wreck your experiment. Okay, so just be careful that when you're defining your outputs, you understand how you're going to measure it and you feel comfortable that your measurement system has the accuracy and the precision that you need to successfully take a measurement. Okay. Now, in terms of defining your outputs and your inputs, this is an incredibly important part of the process. And I want to show you a tool called a SIPOC diagram that you can use to define all of your inputs and your outputs. Now, this SIPOC diagram is essentially the process model on steroids. All we've done is we've added the customers on one end, the suppliers on the other, and this is a tool that we use to essentially define, kind of at a high level, what are our critical inputs, processes, and outputs along with customers and suppliers. Now, I want to do an example where we take a problem and then use a DOE along with a SIPOC diagram to essentially help us identify the root cause of a problem. And let's say, for example, now we own a bakery. We own a bakery shop, and we recently did a customer survey, and the feedback that we got from our customers is that most of our customers are generally dissatisfied with the flavor of our cake. They took our survey and they said the flavor of our cake was below average. Let's now design an experiment to understand the root cause of that problem and make changes to our process and our inputs to get a better output. Okay, so we can do the SIPOC diagram. We know we're a bakery shop. We serve walk-in customers. We have party guests. That's our primary customer. We can also define all of the outputs of our process. These are the things that our customers care about and find valuable. And so our customers tell us they like flavor, texture, color, size, and shape. Those are quality attributes. Those are things about the cake that the customers really, really care about. But when you're defining your outputs, it goes beyond just quality attributes. Yield matters. If you have to bake 2 cakes to get 1 good cake, that's a problem. Lead time matters. If somebody calls you up and orders a cake and you tell them it's going to be done in 3 months, they're going to take their business elsewhere. Cost matters. If somebody calls you up expecting to pay $20 and you quote them $200, they're going to take their business elsewhere. And so things like cost and yield and lead time are also outputs of your process that you could optimize for in an experiment. But of course, today we're focused on flavor. The process is how you transform your inputs into your outputs. And so this is where you would pull up your procedure, your flow chart, and go, okay, we preheat our oven, we mix the dry ingredients first, we mix the wet ingredients next, we combine them, we pour them into a pan, we bake, we cool, decorate, and ship. That's our process, okay? You can also use the SIPOC diagram to define all of the inputs that you have that you know affect flavor or affect one of your outputs. All of the ingredients might affect flavor. Your mixing equipment, your mixing bowls, your cake pan, the oven itself, your baking temperature, your baking time, even the bakers themselves are all factors that we all agree might affect the flavor of a cake. Okay, so those are all important inputs. Then we can also talk about the suppliers, and this is an important piece. Where do we get our inputs from, right? Is it different raw equipment vendors? Is it home goods stores? Is it grocery stores? Where do we get our suppliers? And I'll show you later on in the presentation why that matters in terms of blocking out certain factors. Now, when you're looking at the SIPOC diagram, obviously your outputs are your response variables. And so we're going to do an experiment where we're going to optimize for flavor. And the way that we're going to do that is we're going to make changes to some of our controllable factors. And again, as a team, remember this is a team sport. We're going to sit down as a team. We're going to go, okay, what are the 2 or 3 most important factors that we think have a strong relationship to flavor? And as a team, we decided that we're going to study baking temperature, baking time, and one of the cake ingredients, which is sugar. Okay, so we're going to build an experiment to essentially improve the flavor by changing sugar, baking temperature, and baking time. Okay, that's going to be our experiment. Now, before we move on, we have to talk about this really important term called a level. So here's kind of our experimental objective. We are asking a question. We are going to perform an experiment to identify which combination of input factors, temperature, time, and sugar, produces the best output. And for us, that means the best tasting cake. And so again, we're going to sit down as a team and we're going to go, okay, we have 3 factors that we're going to study: temperature, time, and sugar. And what we need to define for our experiment are the different levels that we're going to include in that experiment, okay? And that term level essentially just means a specific setting or set point of that factor. And so for this particular experiment, we are going to do what's called a 2-level experiment. So for each factor, temperature, time, and sugar, we're going to define a high level and a low level. And typically, if you're looking at a design matrix, the high level is designated by the plus sign, the low level is designated as a minus sign. And again, we're going to sit down as a team and we're going to define exactly what those levels are. So the high level for temperature would be 400, the low level is 350. The time, the high for cook time is 20 minutes, the low is 15. For sugar, it's 3 cups at the high, 2.5 cups at the low, okay? Now we essentially need to take all these factors and all these levels to determine what combination of input factors gives us the best tasting cake. okay? And so this is where we're going to start to design our experiment. And so, for example, we might find at the output of our experiment that the best combination of input factors is temperature at the high, time at the high, sugar at the high, okay? And you'll notice here in this design matrix over here, I'm introducing a new term called a treatment. A treatment is defined as a unique combination of factors and levels within an experiment. Treatment group number 1 is temperature at the high, time at the high, sugar at the high. Now, that's not the only treatment group that we're going to run. We might run a different experiment with temperature at the high, time at the high, sugar at the low. We would call this treatment group number 2. And again, it is a unique combination of factors and levels within our experiment. We might have a third treatment group where we run temperature at the high, time at the low, sugar at the high, right? We're gonna call that treatment group number 3, and that is again a unique treatment group. Same thing here for treatment group number 4. Temperature at the high, time at the low, sugar at the low, and we're essentially going to build out this design matrix that defines all of the different unique combinations of factors and levels within our experiment. And again, the whole point of this DOE is we're gonna build all these different unique combinations, and what we're looking for is the best tasting cake across all of these unique combinations. Okay, so this is called a design matrix. Now, before you execute your experiment or while you're designing it, one of the most important terms that you need to understand is the idea of error. Okay, error is one of the most important concepts in a DOE, and there's 2 types of error. The first type of error is called systemic or systematic error, and it is essentially any variation in your response. And remember, for us, our response is taste. Any variation in the taste of our cake that has a special cause outside of the process being studied. Let me give you some examples of systematic error in this idea of baking a cake. If we baked cakes and we had bad eggs, that would be systematic error. That would affect the taste of our cake, and it would have a root cause, or it would have a special cause outside of the process being studied. If we were using expired milk or a broken mixing paddle, or we weren't actually following our procedure, or maybe we had hot spots in our oven, all of those sources of variation would affect the flavor of our experiment. It would affect our response variable. And your job as an experimenter is to eliminate systematic variation. This will completely wreck your experiment, and it should be eliminated. You should make sure before you ever run an experiment, you're not using expired milk, you're not using bad eggs, your mixing paddles is not broken, everyone's following procedure, you don't have hot spots in your oven. Make sure to eliminate all of that systematic variation. Okay, that's number 1. The other source of variation is a little bit tougher to deal with, and this is called random error. This is essentially any variation that is caused by either controllable or uncontrollable factors, or simply just random variation in the response variable, okay? And to explain random error, I want to go back to the list of input factors, right? We've got different cake ingredients, we've got mixing equipment, cake pans, the oven. Imagine for a second, you're looking at a bunch of eggs. If you opened up a carton of eggs and you looked at 12 eggs, those eggs will slightly differ in size from one egg to another. There's going to be some random variation in those eggs that will change the volume of the egg content that actually goes into the batter. Okay, that's called random variation. The same thing might be true if you scoop a cup of flour. If you don't perfectly skim the top, or if you don't pack down the flour, every time you take a scoop of flour, it might vary slightly from one scoop to another. That's called random error. The same thing is true for your measurement systems. I talked about gauge R&R. If you're using a measurement system that has poor gauge R&R, that lack of gauge R&R, that measurement system variation, will introduce error or random variation into your experiment. So that's why it's really important that when you're defining your measurement system, you're picking a measurement system that has good precision so that you're reducing the random error in your measurement, okay? Now, the analogy here that I like to use is common cause variation. So when I talked about systematic error, I talked about special cause variation. If you're familiar with control charts, special cause variation has a root cause outside of the process being studied. Random error typically comes from just expected variation from the other factors that might affect flavor. Now, random error is incredibly important because as we run our experiment, that random error is going to show up in our final analysis as the mean square of the error. In fact, if you're not familiar with ANOVA, I did a whole separate video on ANOVA to explain how ANOVA analysis works. Go check out that video. I'll link to it in the description below where I talk about the mean square of the error. the most common analytical tool that we use for a DOE is oftentimes ANOVA analysis. And essentially in ANOVA, we're trying to determine whether or not our factors are having a statistically significant impact on our response. And the way that we make that statistical conclusion is by comparing our variation between treatment groups against our variation within a treatment group. And so our goal as an experimenter is to reduce random error in our experiment. If we have too much random error, again, it will wreck our experiment and essentially waste all of our time and waste all of our effort. And so what I want to talk about now are two of the most important concepts in the world of DOE to help eliminate or reduce random error in an experiment. And here's the expression, okay? I think this is the most important expression in the world of DOE. In fact, if you disagree with me, leave a comment below. But here's the expression. Block what you can, randomize what you can't. This is one of the most important phrases that you'll ever hear in the world of DOE, and it's the best phrase that you can use to address the random error in your experiment, okay? Let's start with blocking because there's an order to this. Blocking is the preferred method, and when you can't block, you randomize. Okay, that's the expression. Block what you can, randomize what you can't. Let me explain what blocking is, okay? In the world of DOE, blocking is a method that we use to reduce or minimize the variation or the random error in our experiment, where essentially we identify factors that we know are going to affect our response, and we run our experiment at essentially a single set point or a single level for that factor, okay? Now, if when you were designing your experiment, if you use the SIPOC diagram, this is the time to pull it out and identify factors that need to be blocked out. So again, if we go back to our SIPOC diagram, we know, or we already acknowledged, that the bakers themselves can introduce variation into the taste. The type of oven that we're using, the type of cake pan that we're using, the type of mixing equipment that we're using, all of those factors, that the vendors that we buy our raw material from have some variation to them. All of these, there are a ton of other factors that could affect flavor, but right now we don't care about those factors. We agreed, based on our experimental objective, we agreed that the three factors we want to study are temperature, time, and sugar, and we don't care about all of these other factors right now. And so what we're going to do is we're going to block them out. Okay, so let me give you an example of this. Again, let's say we've got Tommy and June here. Okay, we've got two people, and we know based on their experience that June bakes cakes that are slightly better than Tommy. Okay, we're going to block out this variation. We're going to bake all of these cakes, this entire DOE. All of our cakes are going to be baked by a single person. We are going to essentially block this factor out. And by blocking that factor out and running our experiment with this particular factor at one level, we're eliminating all of that person-to-person variation, and we're essentially reducing the error in our experiment. If we ran this experiment with two different people baking the cakes, we'd see a little bit more random error in our data set, and we want to block that out. The other example might be cake pans. You might recognize that when you bake a cake in a larger cake pan size, that you get some variation there in terms of flavor. When we execute this experiment, we're going to bake all of our cakes in the same size pan to essentially eliminate any of that pan-to-pan variation and block that factor out as a contributing factor to our experiment. Okay? The mixing equipment is the same conversation. Sometimes our people use industrial grade equipment. Sometimes they might use a hand mixer. And we know, discussing this as a team, that we might sometimes experience variation between our mixing equipment. And for the purposes of this experiment, we're going to block that factor out and essentially eliminate any of the equipment-related variation. We're going to bake all the cakes using the same mixing equipment to eliminate that as a source of variation, okay? The same thing is true for raw ingredients. Let's say we buy eggs from two different vendors, and we know that those eggs are slightly different from one vendor to another. We want to block this factor out. We're going to build all of our cakes using the same raw material vendor and the same raw material batches so that we can block out or eliminate any of that raw material variation that we don't care to study in this experiment. Now, you might be sitting here thinking, Andy, the vendors matter, the equipment matters, the baking pans matter. Yes, that is true. But in this one experiment that we set up as a team, we agreed that we're going to study temperature, time, and sugar, and right now we don't care about some of these other factors. We could run another experiment down the road where we studied raw material or the mixing equipment or the baking pans. We could study that in a future experiment, but for now, we don't care about those factors. We're going to block them out, okay? The last example might be oven types. Maybe some of your ovens are convection ovens, some of them are more conventional ovens, maybe you've got a double oven, something like that. And again, for the purposes of this experiment, we're going to bake all of our cakes using the exact same oven so that we can block out all of the variation that might come from oven to oven. And when we block out all these factors, the point of that is to essentially eliminate all of that variation so that we can truly study the factors that we care about, which for the purposes of this first experiment is temperature, time, and sugar. Okay, so blocking is one of the most important concepts in the world of DOE. Identify the factors that you care about, but also identify the factors that you need to block out so that that error doesn't wreck your experiment. Okay, that's really, really important. You know, I gave you that expression, block what you can, randomize what you can't. Now we have to talk about randomization. When you do a DOE, let's say we're baking all these cakes, you're going to run your experiment in a particular order. Okay, and that term order just simply means the chronological sequence in which you're going to execute your experiment. And one of the best practices in the world of DOE is to essentially randomize the order in which you're building your samples, your DOE samples, to essentially spread out or make sure that if there is some uncontrollable source of variation that's affecting your experiment, that variation essentially gets spread out evenly across all of your different experimental groups. So, for example, let's say this is our design matrix. We're going to build 8 different treatment groups, temperature, time, and sugar. And for each of those treatment groups, we're going to build 4 replicates. A randomized design is essentially, and Minitab will do this for you, it'll tell you in what sequence you should build all of those cakes. And again, the reason that we use randomization is that if on the off chance there's some uncontrollable source of variation out there, that variation gets kind of spread out evenly across all the different treatment groups. Now, the other concept in the world of DOE that's incredibly important is the idea of replication. If you run an experiment and you get a favorable result, you should be able to run that experiment again and essentially replicate that result. In fact, this kind of relates to the sample size. When you're designing an experiment, you should define how many replicates, how many samples you're going to produce of each treatment group for that experiment. And the reason that that's so important is because adding additional samples or replicating your DOE essentially provides for degrees of freedom in your ANOVA analysis. Remember, ANOVA is one of the primary tools that we use at the end of a DOE to evaluate whether or not the factors that we're studying have a statistically significant impact on our response variable, okay? And the way that we evaluate the mean square of the error is through replication. We want enough samples to truly get a fair, accurate representation of the mean square of the error. The other thing that replication does for us is it gives you additional degrees of freedom if you want to evaluate interaction effects, which is a whole nother video. It's a whole nother concept. If you want to evaluate your interactions, you have to have degrees of freedom to do so. And so the only way to make that evaluation is to replicate your experiment and give yourself the degrees of freedom that you need to do that. Now, I talk about replication and sample sizes, but I also want to remember, like if we're talking about ANOVA analysis, remember ANOVA is a type of hypothesis test. And anytime we're doing hypothesis testing, there is a chance that we come to the wrong conclusion. There are errors that we can make in ANOVA, and particularly 2 errors, type 1 error and a type 2 error, okay? Now, I also want to relate this back to a concept in ANOVA or a concept in hypothesis testing called power. When we do a hypothesis test or when we do a DOE, we want our experiment to have power. And the definition of power is essentially the idea that we can correctly reject the null hypothesis when it is false. If temperature and time and sugar truly affects flavor, we want to be able to make that conclusion. And a high-powered DOE allows us to correctly make that decision, okay? Now, in a DOE or in ANOVA, the best way to improve the power of your experiment is essentially to increase your sample size. Take more replicate measurements, and that'll give you more power. It reduces the likelihood of a type 2 error, and it gives you the degrees of freedom to also estimate any interaction effects in your experiment, okay? Okay, real quick, let's recap. If you're going to design a DOE, number 1 is make sure you and your team understand the experimental objective. Why are we doing a DOE? What is the problem that we're trying to solve with this exact experiment? And based on that experimental objective, you can identify the response variable that you're going to measure at the conclusion of your DOE, along with the measurement systems that you're going to use to essentially measure those outputs. And those outputs can be anything. dimensional attributes, yield, lead time, cost, process capability, all that should be based on your why. We are running this experiment to understand the root cause of our problem, to optimize our process, to improve OEE, to reduce lead time. All of the outputs that you measure should be based on your why. Then you should identify the critical input factors that you want to study to improve your output. And again, it could be raw material, it could be energy, it could be equipment, information, people. There are factors you want to study, and there's factors that you must block out to make sure that those factors don't wreck your experiment. That's an incredibly important part of the process. And really, that was the whole point of today's lecture, is understanding your outputs, your inputs, and using blocking and randomization to address random error. The next part of the DOE process is to essentially identify what type of design you're going to use. Are we going to use a full factorial design? Or are you going to use a fractional design? And again, a lot of that depends on your experimental objective. Step 5 is running the experiment. Step number 6 is a lot of the analysis. So we briefly talked about ANOVA. We haven't talked about main effects or interaction plots. Maybe that'll be the topic of a future video. And then lastly is kind of rinse and repeat. DOE is a lot like Plan, Do, Check, Act. It's an iterative process where we should be performing more and more experiments to better understand our process and better understand our outputs. The iterative approach to DOE is the right approach to take in kind of the world of DOE. That is it for today. If you're looking to grow as a green belt or a black belt or a CQE, I've got a ton of great resources that can help you on your journey. Greenbeltacademy.com/free course, greenbeltacademy.com/free black belt course. I've got a bunch of great courses that will help you learn and grow and prepare for these exams, video lectures, practice exams, all sorts of downloadable content to, again, help you prepare for any of those exams. By the way, do me a favor. If you like this video, hit the like button so that other people just like you who are on one of these journeys can find the same content and learn and grow. And then if you want to stay on this journey, hit that subscribe button. That way, as I publish new content, you get notified and you can learn and grow and prepare for the Green Belt exam. Anyways, thanks so much. I'll see you later. Bye.